Okay, this is test one at 4:50 in the afternoon, and this is a looms Kelvin test of a metal halide bulb from a fish tank operation. So we're going to check it on regular AC power first. The bulb is cold, room temperature, and the power supply. So we're going to start it up from scratch and see how many watts and looms the bulb takes over Faraday and Tesla, and then we're going to run it on the 4-phase superconductive grid power to see if we get more looms, less watts, colder temperature, and so forth and so on. But we'll do this test first. Okay. If it doesn't blow up, that's fine. Oh, by the way, you should always clean these with alcohol before you start them. Okay, our load is 180 watts, 188 watt, 190 watts, 198 watts, and the bulb is a little bright. So now we're going to check the lux reading of that.
Still warming up.
It's still warming up. It's nice and bright. A little suntan.
Mm-hmm.
Okay. So it says that the Kelvin temperature is 1900 and the looms are 15,000. Yeah. It needs to be on the higher setting. Okay, so the penetration is coming back. Okay, let's see what the wattage is. 287 watts. And the temperature very difficult to see the temperature. Okay, there we go. Let's get right up on it. 354 degrees. 300 watts. And hear the ballast humming. We're going to run it on the 4-phase power in a moment, but then we're going to run it directly off of the superconductive circuit, linear magnetism. But we're going to do this first just to give it a step up and see where we're at so we can have a little control. It's bright, that's for sure. 392. And looks like it's pretty much calmed down at 280 watts. 288 watts. Hertz and 2.4 amps at 119 volts. So we're going to match the voltage for sure, but we're definitely will be up in frequency. And we'll see what the watt load is. 295 watts. So apparently this is the problem with metal halide. The longer it runs, the more heat that the ballast takes up and makes them inefficient. That's what we're going to try to accomplish. We're going to run a test off the genset, 4-phase grid. Then we're going to run a test directly off the hydro-Me linear pole magnetism circuit through the ballast, and then we're going to run just the bulb without the factory ballast to see the difference between those two. And these bulbs can take a tremendous amount of brunt of energy, and they're going to need it. When we go directly off the circuit, it's an energy density. And then that'll give us a determination what we can actually get out of a metal halide bulb. My understanding is these are much more efficient than we're led on to believe, because it's the ballast that's causing the efficiency deficit. And if we can just get rid of the ballast and go directly to the bulb, like we've proven with a regular incandescent bulb, then it's a better play for us. And a metal halide light combined with a sodium vapor light in a warehouse is, everybody knows, those two light standing waves is a more natural, healthier light for us over fluorescent. But they suffer from energy losses, and that's why they're only in a hobby base like a fish tank that needs that penetration and that depth of light. So the next thing that we need to do is come up with a basic footprint of tile on the floor. 1, 2, 3, 4, 5. We'll stay at 5 tiles from the light source, and at 5 tiles we have 1500 lux 1500 lux at that distance. If we go closer, it's more, but it goes off scale. So we'll just stay at 5 tiles right at 5 tiles off the floor. Very scientifically not accurate, but 1500 looms. Okay. The amps 290, the volts, the watts 295. The voltamps, the watts are 289. The volt amps is 295. That's the power consumption. The amps is 2.4 volts frequency, and we've only been running for a couple minutes, so watt hour doesn't really matter right now. But that's what counts, is these readings right here. and hertz. And then finally, whatever the final temperature is after 10 minutes should give us a definite heat soak. Okay, so the bulb is at 420 degrees and we're at 10 minutes and 19 seconds into this first control run. Okay. Now let it cool down. Okay, we got it. Okay, now we're changed the power. That was Tesla Faraday. Now we're on Puckta. Okay. So I'll put a little plug for Puckta gaseous fuels and energy. And then that's going to be hooked up to the fluorescent light. And we'll go back over the standing wave principle and the fluorescent light in a moment. Let's turn on the power. Got our voltmeter here to tell us our frequency and volts. And as you can see, once again, the generator is not turning, but it's producing voltage. That's the definition of superconductivity, is free electrons. And watch, I'll just move the generator a little bit. Just like that. And watch the voltage. You can see it's definitely coupled to the generator. And we're just barely moving it. Okay. So now we're going to see what temperature or what voltage that metal halide will fire at. Okay. So we're at 45 volts and the fluorescent light has fired. Okay, 50 volts and the fluorescent light is fired. And you can see so this needs to turn on at a certain voltage, apparently. So our frequency is already 30 volts, 30. Okay, so this turned on. It's just about ready to turn on. Okay, so 60 hertz, 50% perfect power. 70 volts. The fluorescent light is definitely fine with that. Okay. Here's our frequency. Here's our watts. Here's our amp. Here's our volts. But I think this has to cool down before it'll restart again. The cooktops are all on, so we balance the load in the generator. What's the temperature of the bulb? Okay. Yeah, I think they have to cool down before they'll start again. Alright, so we're going to give this a couple more minutes because I've only got 30 minutes of recording time. And if I don't see it start up in a couple minutes, yeah, keep cooling it down. Then we'll just wait and start the video again in part 2. But I want to give it a couple of minutes first, so we can have everything on one video. In the meantime, you can look at that. The standing waves in a fluorescent light. Pretty.
You can't see it normally.
No.
You can't see it.
Yeah.
The camera detected it, but now we can't see it.
And a regular fluorescent light does not do that.
Oh wow.
Okay? It's because of this power. That's so much more healthy for you because it locks the energy inside the plasma versus letting that energy release in the electromagnetic spectrum to hurt you. It's now bound in the plasma, and that's the empirical proof of that.
What's that difference?
Huh?
What difference speed?
Yeah.
Get close to that one, real quick.
Because it's how the ballast is wired. Everything is in. That's the beauty of this energy platform, is that everything is in proper order on the atomic level. And that's the beauty of superconductivity. Everybody's in order. What temperature? pretty close. It should fire.
Regular temperature.
There we go. Look at the color already.
Yeah.
Look at how blue that is. That is cool. I told you there's a play with xenon and superconductivity. Do me a favor. Go over to the desk and grab my safety glasses for me. Wow. That is cool. I'm glad we waited. Look at the fluctuations of the light versus what it was before. Look at the wave pattern the light's making. Yeah. That is way different. Okay. Stand back here. Okay. 600 looms, but we're still cold. Okay, let's see what the amps are. Oh, look at that. We're only drawing 100 watts. Look, that's 3 times less than we were drawing before. Oh no, that's volts, I'm sorry. I got all excited. Oh, 135 watts versus almost 300 watts. Okay, now the amps. 3.7 amps, 100 hertz, watts, amps, volts. So go right up on it. 230 degrees temperature. We were at 400 before. So we're at 110. What volts were before? 110? What? About 110, right? All right, so we'll just leave it there. But look at that. That is pretty. So now we've created a plasma standing wave in a metal halide light. The same as that. And we have 136 watts. That's fucking cool. Okay. Uh-oh. I think I bumped the plug. Okay, that's a good enough empirical test for now. Okay, we're going to take this to the next level. But there's your first run of a metal halide bulb. Thank you for watching.